Page 125. All right. It says a fast. So remember, we're starting to put things together to make sure it's in sequence. So it says fast food restaurant offers 3 different kinds of hamburger: hamburger, cheeseburger, bacon cheeseburger. Sounds good to me. I'll take one of each. Historically, half the burger sales were hamburger sales, 1/4 were cheeseburger, and 1/4 were bacon cheeseburger. Has the sales distribution changed recently? A random sample of 160 sales shows the following: 102 hamburgers, 34 cheeseburgers, 24 bacon cheeseburgers. State the null and the alternative. Make a chart showing the observed. Okay. So we're going to call mu. This is going to be burger sales. So our null hypothesis, we would just say that mu sales the same, and then we could say the alternative, mu sales are different. Okay, and then if we want to make a chart based on this, so we have hamburger, cheeseburger, and bacon cheeseburger. Do you understand H, C, and B? Hamburger for H, cheeseburger for C, bacon cheeseburger for B. Hello. All right, so they had said this is what historically they have shown this. They said half their sales were this, so that's 0.5, and it says 1/4 were cheeseburgers, which is 0.25, and I'm just making a decimal. I don't know if I need the decimals or not later. And then the bacon cheeseburgers, 1/4 and 1/4, so 0.25, right? So this is what the restaurant has realized through many years of sales. This is what they typically run, and then they observed they had a random sample of 160 that had done, and so they had realized that this was 102 out of 160. This was 34 out of 160, and then this was 24 out of 160. And so now it's going to make sense of why we did the decimals, because I'm just going to convert the fractions to decimals. So if I go 102 divided by 160, that comes out to 0.63, 0.36375. This comes out to 34 divided by 160, so 0.2125. And this one, 24 divided by 160, is 0.15. Okay, so things that are items that make you go, okay, there might be something there. We're basically looking, is there a difference between those two? It appears to be. Is there a difference between historically and this? It appears to be. Is there a difference between this? Oops, close. Undone. Okay. Is there a difference between this and this? And they all appear to be slight differences between them, but was it coincidental that 160 made a difference? You know, what had happened with any of those things? Bus must have got here. I'm just kidding. He's like, yeah, Stirrup, I drive a bus. Okay. All right. We're on page 125. So we are now done with problems number 1 and 2. Okay. Now, so this historically is basically, we could have also called that the expected, because we've used all of our data to get that, and then our observed is still can be observed. So, but that's basically what takes place with this information. Okay. All right. So let's move down to the bottom. So page 125. And again, if you just got here, we're going through the homework that was assigned. If you're here, please copy it down. This would be vital for you to use on quizzes and tests for the remainder. Okay, if you're here, you're getting the points for it. If you're not here, you got to make sure you watch the video and show me what you did. Okay. But at the bottom, for problem 3 and 4, it says all 12 zodiac signs are equally distributed among the population. Now we're going to get the student that's going to tell us that there's no longer 12 zodiac signs, but there's actually 14 now. Okay. I have no idea. I know that people follow zodiac signs all the time. People are like, oh, you're a Capricorn, you must do this. Okay. No, I don't do that. So, but it is what it is. All right, so the 12 zodiac signs are equally distributed among the population. A random sample of 200 people is conducted. Okay, so we have a random sample of 240 people. We have the 12 zodiac signs, which are basically the year broken up. And then if you fall between these certain dates, you happen to be this, these dates, this is that. State the null and the alternative. So we're going to say that we'll call mu as the zodiac signs. So my null hypothesis would be mu is equal spread. The alternative, mu is not equal spread. Meaning you should have an equal amount of people on each of the zodiac signs. That's basically what they're trying to aim towards. Okay? What will be the expected value for the 12 zodiac signs based on our random sample of 240? Okay. So, I apologize. I don't know the 12 zodiac signs, but I'm just going to do this. Okay. I don't know what the 12 zodiac signs are. I'm sorry. I know there's like Capricorn, Cancer, Libra, and I don't know anything else, and I'm sorry. Yes, I'm sure I've heard them. If you could repeat them to me, I'd be like, oh, yeah, that's right. You could make up some other Greek-sounding word, and I'd probably be like, that sounds good, too. So basically what they are looking at is they think that each one of these is a 1 in 12 chance. You have a 1 in 12 chance of any of these taking place. So that means that we have these 240 people. So we would expect, if this is a true statement, that you would have 20 people in each of these category of my 240 people. Okay? So I'm basically just going 1/12 of 240. It's 20. Okay, so that's kind of what you're expecting. Now, we haven't gone any farther on this to make sure, is this a true representation of it or is it not? I don't know. Okay? Now I'm on the back page, page 126. Am I going too quickly or am I doing okay? So it says, sales of Starbucks gift cards for the past 10 years have been stable, broken down as follows. So you have $10, $20, $30, $50 denominations, and then the percent of each of the denominations is given. Okay. So they have done that. And it says a large new Starbucks ad campaign is conducted to increase sales of the larger denominations. A random sample of 1,000 gift cards is obtained. The breakdown is as follows. So our sample is 1,000 random people. That's a really great sample size. And they had as follows. So number 5, we're going to create our null and our alternative. So I'm going to say that mu is going to be gift cards. And then my null hypothesis is going to be mu is equal to past 10 years. and then our alternative mu is not equal to the past 10 years. So you might start seeing on some of this, I've kind of flip-flopped having the equal sign as equal and non-equal. It's kind of flip-flopped from what we've seen in the past, but that's okay. We can still work through it. That things do change. So they have noted, so create a chart to show this. So we have the $10, the $20, $30, and the $50 cards. These are all cash amounts. I made them green for a reason. This was the past or the expected. So they had, and these are all in percents. So we had 52%, 30%, 10%, and 8%. And then they said that our observation, they had, and I'm going to make this so you had 460, and we're going to go 460 out of 1,000. We'll make that a percent. 280 out of 1,000. We'll make this a percent as well. 180 out of 1,000. And 80 out of 1,000. And so that comes out to 46%, 28%, 18%, and 80 out of 1,000, and 8%. Okay, and again, things that we're going to start thinking about, did these values here and here, was this coincidental? Did our ad campaign work? I mean, kind of looking at it, if their ad campaign was trying to get, oh, you know what? 80 out of 1,000. This is 0.8%. I'm sorry. This is 1.8%. Or no, that was right. 800. That was right with 8%. I'm sorry. My mind's going elsewhere. All right. So create that. So for which denomination was observed the expected value the same? Does this suggest evidence? Well, being that these two are the same, and their ad campaign was trying to get more people to buy the higher denomination of gift card, you know, did it work? I don't know. There's not enough validity to this to say it worked or it didn't work. Okay? All right, so that's 7.1. All right. May I move on? Are we okay? Life's good? Everyone's happy? Okay. I am now going to be on page 49, so use some notes. Okay, this is called the chi-square statistic. Now I'm going to show you. So they use this weird looking X to mean chi-squared. It's not tough to do, especially because I'm going to show you how to do this on Desmos. It's going to make it a lot easier. But this is basically the chi-squared. So you have the observed minus the expected quantity squared, all divided by the expected. Okay? So now this is going to take us back. Halfway down, it says the chi-squared value must be a number greater than or equal to 0. When the chi-squared value is 0, it means the observed and expected value were the same. This provides no evidence against the null hypothesis. Chi-squared between 0 and 1 provides little evidence against the null hypothesis, but as chi-squared rises, the evidence grows. The total of all chi-squared values will determine the strength of the evidence in the null hypothesis, and the null will determine whether we reject or fail to reject the null. When we perform a chi-squared test, we need to make a 3-column chart including observed values, expected values, and the chi-squared values. All right. We are not going to not include our best friends, the Desmos family. So let's jump onto Desmos and make this. So it's important that you see how Desmos works with this. Okay. And trust me, Desmos will be a nicer utilization of this. Excuse me. So I'm going to create a table. And I'm going to do 11, 7, 6, 9, and 7. Those are our baseball cards, A, B, C, D, E. And then we are expecting this, 8, 8, 8, 8, 8. Remember this, we had done a baseball situation. So our baseball card from our graph. Now, if you flip over to the next page, you get the 1.125, 0.125, 0.50, 0.125, 0.125. Okay, that is done because you have the observed minus the expected. So watch what I can do here. I'm going to create this column here. I'm going to put this in parentheses, and I'm going to say that my observed is my x sub 1 minus my expected, which is y sub 1, and then we'll go divided by, but I have to make that squared right here first. Oops, get up there. Quantity squared, and then divided by my expected, which was y1. And if you do this, it does your table for you. Okay, that's just the equation. Now you have to realize what your x1 is, what your y1 is. Okay, if the x sub 1 and y sub 1 change to x sub 2 and y sub 2, then you have to change your equation as well, but it's still going to be the same equation. But that is our chi-squared. So since the x squared values measure how unlikely we are to obtain the count for each category if the null is true, the largest chi-squared value above was from card A. This suggests that the null is true, that we got a card A was the most surprising. Okay, the chi-squared value is the final evidence against the null hypothesis. In this case, the chi-squared statistic adds up to exactly 2. So if I were to add up 1.125 and 0.1 or 0.125 and 0.5 and 0.125 and 0.125, that sums up to 2 for an answer. Okay, and that's going to lead us into 7.3, which Desmos is really going to be a powerful tool for us in dealing with that. So what I'd like you to do is I'd like you to maybe take a quick gander at page 127, 128. You know, just take a good look at it and know that that's what we're covering for tomorrow. And then we'll do the 7.3 chi-squared test on Desmos. Good in the hood? All right, so my friends, I will tell you